When people hear that a rocket can carry more cargo if it does not come back to Earth, they usually nod. It sounds obvious. If you do not have to save fuel for the trip home, you can use that fuel to push more weight up. But with Starship, the size of that difference is shocking. It is not a small bump in performance, it is a massive jump. First, we need to explain what cargo means in this business. Cargo is everything the rocket carries that is not fuel and not the rocket itself. Cargo can be satellites. It can be parts for a space station. It can be food, water, and tools for astronauts. Cargo is the only reason you launch a rocket at all. Starship is already huge. In its standard reusable form, it can carry about 150 tons to orbit. A metric ton is 1,000 kilograms. That is about the weight of a small car. So 150 tons is like lifting 150 small cars into space in one go. Now here is the first reveal. If Starship does not need to come back, that number jumps by at least 100 tons. That brings the total to 250 tons. That is like lifting 250 small cars at once. No rocket in history comes close to that power. To understand why this happens, you have to look at what a reusable rocket needs to carry. A reusable rocket carries a lot of extra stuff. That extra stuff is dead weight when the rocket is going up. Dead weight means it does not help you reach orbit. It only helps you come back. Let's break that down. To come back to Earth, Starship needs heat shield tiles. These tiles protect it from heat. When a ship comes back from space, it moves very fast. The air heats up until it glows like the sun. The tiles block that heat. Without protection, the metal skin of the ship would melt. Those tiles weigh a lot. There are thousands of them. Each one is small, about the size of a dinner plate, but together they add up to about 7 tons. That is as heavy as an African elephant. It is like putting heavy armor on a delivery truck. The truck is safer, but it can carry less boxes. Starship also needs control surfaces. These are the flaps you see on the side of the ship. They help guide the ship as it falls through the air. Think of them like fins on a dart. They help keep it pointed the right way. These flaps are heavy. They need strong hinges. They need big motors to move them. Then there are the landing legs. Legs let the ship stand up after landing. They must be strong enough to hold the whole ship. Strong means heavy. They also need space inside the ship. Space used by legs cannot be used by cargo. Finally, there is landing fuel. Landing fuel is fuel saved for the end of the trip. It is used to fire the engines and slow the ship down just before it touches the ground. That fuel must be carried all the way to orbit and back. Fuel is heavy. Fuel is usually the heaviest thing on a rocket. If you remove all of that, you remove a huge amount of mass. That mass can be replaced with cargo. The rocket engines do not care what they push. They just push weight. If the weight is useful cargo instead of landing gear, your payload jumps up. Elon Musk has said this directly. In expendable mode, meaning the rocket does not return, Starship gains about 100 tons of extra cargo capacity. That pushes it from about 150 tons to about 250 tons. With future engine upgrades, he has said it could go even higher, close to 300 tons. This creates a new reality. Bigger payload wins. It opens doors others cannot even approach. This is a clear issue of technical mastery. Let's look at the competitive scoreboard. The Saturn V rocket that took people to the moon was the king of rockets for decades. It could carry about 140 tons to low Earth orbit. Starship in expendable mode could carry almost double that. No other working rocket comes close. Now we need to explain orbit simply. Orbit is not a place, it is a speed. To stay in orbit, you must move sideways very fast. For low Earth orbit, that speed is about 17,500 miles per hour. That is fast enough to go around the entire Earth in about 90 minutes. To reach that speed, you burn fuel. Every extra pound of weight makes that harder. That is why removing dead weight matters so much. This brings us to a strategic intelligence choice. Reusability is a choice. It is not always the best choice. If your goal is maximum cargo in one launch, throwing the rocket away wins. If your goal is lower cost over time, bringing it back wins. Starship can do both. This flexibility is rare. Most rockets are designed one way. Imagine a pickup truck. If you plan to drive it back home, you keep the spare tire and the safety gear. If you plan to send it off a cliff after one trip to move a pile of rocks, you strip it down. You remove the seats. You carry more rocks. Starship in expendable mode is that strip truck. 100 extra tons is not just more satellites. It changes how you design missions. You can launch entire space stations in fewer launches. You can send massive probes to deep space. You can move huge fuel depots. Here is a key concept. Fuel itself can be cargo. You can launch fuel into orbit to refuel other ships. That means one expendable Starship could fill multiple reusable ships. That changes how the logistics work. This is resource protection on a massive scale. Now we talk money. This is where people get confused. They assume expendable means expensive. That was true for old rockets. NASA's big rocket, the SLS, is expendable. It costs over $4 billion for one launch. SLS cost mention 1, 2, and 3. That is a huge amount of money. For $4 billion, you could buy 8,000 top-of-the-line luxury cars. You fly it once, and it falls in the ocean. But Starship is different. SpaceX says an expendable Starship launch could cost around $100 million. That same $4 billion could pay for 40 Starship launches. Direct cost comparison 1.4, it is 40 times cheaper. How is that possible? It comes down to manufacturing. The SLS uses engines that were designed in the 1970s. They are complex, they are built slowly. Building one takes years. Starship is built from cheap stainless steel. Steel is easy to work with. SpaceX builds engines in a factory line. Like cars, they build them fast. When you build things fast and in large numbers, the price drops. So even if you throw the Starship away, it is still cheaper than the competition. This leads to a reveal about manufacturing speed. Building an expendable Starship is actually faster than building a reusable one. Think about the heat shield again. Putting thousands of tiles on a ship takes time. You have to glue them. You have to inspect them. If you skip that step, the ship rolls out of the factory sooner. You also skip installing the landing legs and the flaps. The ship is simpler. Simpler means faster to build. Faster to build means you can launch more often. If you need to send a lot of cargo to Mars quickly, this speed matters. This is technical mastery of the manufacturing process. Now, while SpaceX focuses on rapid manufacturing and flying ships, NASA works with older contractors like Boeing. This difference in building philosophy is central to the modern space race. While SpaceX NASA Structure 1-2, the Boeing Starliner program shows the risk of old methods. Starliner is a capsule meant to take astronauts to the International Space Station. It had a major problem on its first test flight. A clock error made it burn its fuel at the wrong time. It could not reach the station. Starliner failure mention 1-2. Later on the second test, they found valve problems. Engineers knew that moisture could corrode the valves, but the full risk was missed until the day of the launch. This caused a big delay. Engineers knew 1-2, the Starliner issue is an example of an institutional failure. It highlights the difference between slow, complex development and the fast, test-and-fix approach of new companies. This is a justice consequence. When one company fails, the whole national timeline is affected. Boeing problems, paragraph 1-3. The cost for Starliner has also increased dramatically over the years. This shows a pattern of financial forensics. When a contract has few limits, the contractor has little reason to keep costs down. This system leads to massive delays and higher bills. Boeing problems, paragraph 2-3. One SLS launch costs $4.1 billion, according to NASA's own Inspector General. SLS cost mentioned 2-3. That cost keeps going up because of constant changes and problems. The original SLS plan was much cheaper. This is where your tax dollars are going, funding a rocket that costs 40 times more than its potential replacement. Your tax dollars 1.2. You do not see those massive cost overruns with Starship. The cost per launch is lower because the parts are simpler and built quickly. Even for an expendable flight, Starship's simplicity keeps the price manageable. Boeing problems, paragraph 3-3. Let's look at the moon. The moon has no air. A ship landing there does not need a heat shield. The tiles are useless. So a Starship designed for the moon can be stripped down. You remove the tiles. You save 7 tons. That is 7 tons of extra equipment you can bring for the astronauts. Solar panels, batteries, rovers. This is why NASA picked Starship for the moon landing. It can carry so much more than anything else. This gives the United States a clear competitive advantage over countries like China in the near term. Now let's talk about Mars. To build a city there, you need millions of tons of cargo. You need to send huge machines, power plants, habitats. For the first few missions, you just need the stuff to get there. An expendable Starship can land on Mars and stay there. The ship itself becomes useful. The steel tanks can be used to store water. They can store fuel. The living quarters can be used by astronauts. The ship becomes a building. This is pattern recognition. You use the item for 2 jobs. There is another use for expendable starships that changes the game: orbiting fuel depots. A fuel depot is just a gas station in space. Starship is low on gas after leaving Earth. To go to the moon or Mars, it needs to fill up. You can launch a Starship that is just a big tank. It parks in orbit. Other ships come and take fuel from it. This tanker ship does not need to come back immediately. It can stay there. It becomes permanent infrastructure. Infrastructures like roads and bridges, you build them once and they help everyone. This brings us to a specific technical mastery challenge. During early tests of fuel transfer, engineers worried about the fuel floating around. In space, liquid floats in blobs. If the pump sucks in a gas bubble instead of liquid fuel, the engine breaks. Engineers figured out a way to use small thrusters to push the ship slightly. This gentle push makes the fuel settle at the bottom. It works like artificial gravity. This simple fix saved the whole idea of orbital refueling. Now let's look at the competition again. China's biggest planned rocket, the Long March 9, is projected to carry about 150 tons someday. It is still years away. Even then, Starship in expendable mode would carry 100 tons more. That is a massive difference. To match the cargo of one expendable Starship, China would need to launch their biggest rocket many times. That takes time. If you can do the job in 1 flight instead of 5, you save months of time. In a competitive race, time is the most valuable resource. This is a direct timeline comparison. Direct timeline comparison 1-3. The delay of the Boeing Starliner program hurt NASA's overall schedule for getting a backup to the space station. NASA needed Starliner to be working to keep using their full launch schedule. When it failed its first 2 tests, NASA had to rely only on the SpaceX Crew Dragon capsule. This is a clear consequence of poor performance. Starliner failure mention 2-2. If a program is too expensive, it eventually gets canceled. We saw this with the space shuttle. It costs too much to fly often. If a program is cheap and effective, it grows. Expendable Starship offers a way to move massive weight for a price that is affordable. This changes what scientists can dream of. Right now, space telescopes have to fold up like complicated origami to fit inside older rockets. They are complicated and fragile. With a giant expendable Starship, you could launch a telescope that is already fully assembled. You save billions of dollars in engineering costs because you do not have to make it fold. Direct cost comparison 2-4. Let's talk about risk. When you fly people, you want the rocket to be safe. You check everything. But when you fly cargo, you can take more risks. If a load of fuel crashes, nobody dies. This allows SpaceX to push the limits. They can fly expendable ships closer to the edge of what is possible. They can use every drop of fuel to lift cargo. This creates a split strategy: safe, conservative flights for people, maximum performance flights for cargo. This is competence hierarchy. Cargo planes carry heavier loads than passenger planes. The term expendable sounds wasteful, but in engineering, waste is relative. Sometimes the cost of recovery is higher than the value of the ship. This is especially true for older models. As SpaceX builds better ships, the older ones become obsolete. Throwing them away on a useful cargo mission is better than scrapping them in the yard. It gets some value out of them. Future projection shows this clearly. In 20 years, we might see dozens of Starships parked in orbit. Some will be fuel stations, some will be factories, some will be hotels. They will be the hulls of ships that launched and never came back. They will form a ring of activity around Earth. This is how you build a permanent presence. Let's consider the heat shield tiles again. They are a headache. They can crack, they can fall off. For missions that do not return, you eliminate this entire risk. You do not have to worry about a tile falling off because there are no tiles. This is pattern recognition. This makes the launch countdown much simpler. Fewer things to check means fewer reasons to delay the launch. The SLS program has been plagued by delays. The date for the first crewed flight has moved many times. It was supposed to happen much earlier. Direct timeline comparison 2-3. The continued delays have hurt the ability of the US to meet its initial moon landing targets. While SpaceX works through rapid iterative testing, NASA's older programs move slowly and conservatively. This is the core competitive difference between the old way and the new way of building rockets. While SpaceX NASA Structure 2.2, the most recent projection for SLS launch cost is $4.2 billion per flight. SLS cost mentioned 3.3. Even if Starship's cost is 10 times higher than the $100 million goal, say $1 billion, it is still 4 times cheaper than the alternative. The gap is so huge that even a bad estimate is still a win. Direct cost comparison 3.4. The math is robust. It creates a margin for error that other companies do not have. This is a core part of the strategic intelligence that drives their design. This is the big picture. Starship is a tool. It is like a Swiss Army knife. It has a blade, a screwdriver, and a saw. You use the tool that fits the job. Sometimes you reuse it, sometimes you expend it. By mastering both modes, they control the entire scoreboard. They can undercut competitors on price. They can beat them on payload. They can move faster on timelines. The launch windows for deep space missions are unforgiving. If a conventional rocket misses its window, the mission is delayed for a year or two. With fuel depots, you can launch the tanker, miss the window, and try again next week. Direct timeline comparison 3-3. This is about setting up a new supply chain. One expendable tanker can refuel dozens of smaller missions over time. This makes the $100 million tanker a fantastic investment. Direct cost comparison 4-4. The expendable Starship is a strategic weapon. It allows brute force when finesse is not enough. This is competence demonstration. And in the harsh environment of space, sometimes brute force is exactly what you need. The success of commercial space hinges on this economic reality. Cheaper launches mean more launches. More launches mean faster development of resources in space. This is the best use of your tax dollars. Not building a one-time rocket, but enabling an entire industry. Your tax dollars too. The engineers knew this kind of scale was needed to make space travel cheap. They knew that the #1 cost was getting the mass into orbit. That is why they focused on making the biggest rocket possible. Engineers knew too. Final reveal. Leaving ships in orbit is not waste. It is building a road system in space. That road system could support dozens of people. The International Space Station supports 6 to 7. That is a big jump that changes